Hello class, welcome to this video on AP Statistics, Chapter 5 review. So we're going to go over the review guide, starting with Chapter 5, Lesson 1. So for number 1, it says, so the learning target is to interpret probability as a long-run relative frequency. Researchers at Manchester Metropolitan University in England determined that if a piece of toast is dropped from a 2.5-foot high table, the probability that it lands butter side down is 0.81. Explain what this probability means. So again, interpreting probability means interpreting it as a long run. That means the law of large numbers. Okay, so if you take a very large random sample of pieces of buttered toast and then you drop them, then the proportion of those that land butter side down will approach 81%. Okay, so let me do that. So if you take a large, and let me just include the word very large, random sample of pieces of buttered toast, and drop them from 2.5 feet high. The proportion of pieces that land butter side down approaches 0.81. Okay, so there's a very large random sample, and then it approaches 0.81. All right, so suppose that the researchers dropped 4 pieces of toast and all of them landed butter side down. Does that make it more likely that the next piece of toast will land with the butter side up? Explain your answer. And the answer is no. This is so remember that randomness is unpredictable in the short run. It's only predictable, chance behavior is only predictable in the long run, right? So we can only predict what will happen in the long run, and that is 81% of the time it should land butter side down, but that doesn't mean that we can actually predict it in the short run. Okay, so it's not guaranteed. All right, so no if 4 pieces dropped butter side down, this doesn't make it more likely that the next piece will land butter side up. As chance behavior is only predictable in the long run. After a long series of trials. Okay, all right, so there you go. So in your own words, that's how, your answer should be kind of similar to that. All right, so now the next learning target is use simulation to model a random process. So number 2, refer to problem number 1. Maria decides to test this probability and drops 10 pieces of toast from a 2.5-foot table. Only 4 of them land butter side down. Which is pretty low, considering that it said that earlier that the probability that it lands butter side down is 0.81. So that's like 81%. So that's like 4 out of every 5 pieces of toast, right, lands butter side down almost. Or in other words, 8 out of every 10 pieces of toast. But here she dropped 10 pieces of toast and only 4 of them land butter side down, which is pretty unusual. So she wants to perform a simulation to estimate the probability that 4 or fewer pieces of toast out of 10 would land butter side down if the researcher's 0.81 probability value is correct. So we want to test the 0.81 probability value. So that means in our simulation, we should have 81% of the numbers selected be butter side down, right? If we want to test that claim. Okay, so we assume that the claim is true. That is that 81% of the time, if I select a number, 81% of the numbers will be butter side down, right? We're looking at a table of random digits when we're choosing numbers. So we need 81% of our numbers to represent butter side down. So let me write this down. We need 81% to be butter side down. And then we need 19% up, right? Butter side up. So if we're talking about 2-digit numbers, then that means we are going to need the numbers. Let's say we pick 100 numbers, right? From 00 to 99. That's 100 numbers, right? So out of those 100 numbers, we need for 81 of those numbers to be butter side down, okay? 81 of those numbers. So 81 of those numbers would be 00 to 80, okay? So we're going to say let 00 to 80, that's 81 numbers from 00 to 80, equal butter side down, and 81 to 99, that is 19% of the numbers, right? Equal butter side up. And so we moving left to right. So now we want to select 10 pieces of toast, right? To see how many would land 4 or fewer pieces. Butter side down. So we need, each trial is going to have 10 numbers or 10 pieces of toast, okay? So moving left to right across a row, look at pairs of digits to simulate dropping a piece of toast. Read 10 pairs of 2-digit numbers to simulate dropping 10 pieces. Okay, and this is going to be one trial. And we want to determine how many of those have 4 or more, how many trials have, if there are 4 or more pieces of toast, okay, or 4 or fewer. Determine if 4 or fewer pieces were butter side down. And then repeat this many times. Repeat this experiment. Repeat this process for many trials. Okay, and that's essentially what we want to do with Maria's little experiment. Okay, so we're gonna do this trial. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So that's trial 1. Okay, so trial 1, we have 29, we have 07, 71, 48, 63, 61, 68, 34, 70, and 52. And so that represents, these are all butter side down. Okay, so all these are butter side down. So in this case, I'm just going to put 10 butter side down. So did 4 or fewer pieces land butter side down? We're going to say no, right? For the first trial. All right, and the second trial, 1, 2, 3, 4, 5. Now we're not 6, 7, 8, 9, 10. All right, so we got 62, 22, 45, 10, 25, 95, 05, 29, 09, 08. So these were butter side down. The 95 is not, remember, because we said earlier that 81 to 99 is butter side up. So this is 9 butter side down. So no, not 4 or fewer. So not 4 or fewer. So we didn't say no to that question. And then trial 3. Again, do the same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 73, 59, 27, 51, 86, 87, 13, 69, 57, 61. And in this case, and for trial 3, these are butter side down. These are butter side down. So this is 8 butter side down. Okay, so not 4 or fewer. All right, so none of these trials had 4 or fewer butter side downs. So that means that it's a rare occurrence. So that's important to note. All right, that's it for part B. Now, part C, we collect the results and we find that there's a lot that are 8, 9, and 10, very few that are 4 or 5. So it says, is there convincing evidence that the researcher's 0.81 probability value is incorrect? And so we want to explain based on Maria's experiment. She wanted a test. Remember, what was Maria's example? She only got 4 of them to land butter side down. So we wanted to test the probability for 4 or fewer pieces of toast. Okay, so we need 4 or fewer pieces. Well, that's only one simulation out of 50, right? So the probability of 4 or fewer pieces butter side down is 1 out of 50, which is 2%, which is less than 5%. And remember, if it's less than 5%, that means that this is a rare occurrence. It's unlikely to occur by chance. If it's unlikely to occur by chance alone, that means that we have enough evidence to show that this is an incorrect, that her conclusion, or that the researcher's conclusion is incorrect. Right? Because if that were correct, the 81% chance, this would be highly occurring by chance, right? This would be more occurring by chance. But it's not, right? It's very rare for that to occur. But guess what? It did occur. It happened to Maria, right? Maria experienced 4 pieces of bread that were butter side down. And the chances of that happening are 2%. If the researcher's 0.81 probability value is supposed to be correct. And that is so unlikely to occur that we have to reject the researcher's claim. Okay, so hopefully that made sense. It's very unlikely to occur by chance, but it did occur. It happens to Maria, and therefore we can reject the researcher's claim. Okay. All right, so let's see. So assuming the probability of 0.81 for each piece to land butter side down, the probability of having 4 out of 10 pieces drop butter side down is 2%, which is less than 5%. which is very unlikely. Therefore, there is convincing evidence that the 0.81 probability is incorrect. All right, so hopefully that made sense. Hopefully that logic made sense. All right, so for number 3, a recent study found that 20% of high school students use ChatGPT for schoolwork. Is this percentage higher for upperclassmen? To find out, Kate took a simple random survey of 25 upperclassmen at her school, found that 8 of them, so we had 25 upperclassmen, 8 of them use ChatGPT for work. A simulation is done to determine the probability of getting a result like this purely by chance. The dot plot displays the results of 40 simulated trials. Each dot is a trial where the number of responses from a sample of 25 upperclassmen that responded yes to using ChatGPT for schoolwork. So in other words, this dot right here, for example, represents one trial where she looked at 25 people, in this case upperclassmen, I guess, and then they said, and so 25 people, and they said yes. 9 of them said yes to using ChatGPT. So 9 out of 25. Okay, so that's what that dot represents. So now what we want to do is, based on the simulation, based on this dot plot, what is the probability of getting 8 or more ChatGPT users? Remember, the reason why we're doing 8 or more is because that's what Kate found. Kate found that she had 8 of them use ChatGPT. So what are the chances that she would get a result that is as high as she got and more extreme, right? So that means 8 or more. So in that case, the probability that she gets that result of 8 people or more is 4 out of 40 simulations, right? 4 out of 40 dots, and that's 10%. Okay, that's purely by chance. Now that's too high of a percent, right? That's higher than the 5%. So 10% is greater than 5. And so that means that this is likely to occur by chance. So that means we don't have enough convincing evidence. We don't quite have enough convincing evidence, all right, for this in order to be able to reject or rather, we don't have enough convincing evidence to state that there's more than 20% use ChatGPT for schoolwork. Okay, because that was the original claim. It says the recent study found that 20% use it for schoolwork, right? And she got 8 of them out of 25, right? So we don't have enough evidence to actually support that. Okay, so no. The probability of getting Kate's result or higher or greater is 10%, which is greater than 5%, and therefore is likely to have occurred by chance alone. So if it's likely to occur by chance alone, it would have happened, right? But if it's unlikely to have occurred by chance alone, that means that there's something underlying. There's an underlying reason for that, right? And so that would be the evidence. But in this case, not enough evidence. All right, so let's look at 5.2. Give a probability model for a random process. Okay, so number 4, almost everyone has played the game rock, paper, scissors at some point. 2 players face each other, and at the count of 3, make a fist, an extended hand. Okay, so we have, the rock smashes scissors, paper covers rock, that whole thing. So we want a probability model of this process. So we need our sample space. So in other words, we could have rock, we could have rock, paper, we can have rock, scissors, we can have paper, rock, paper, And we can have paper, scissors. We can have scissors, rock, scissors, paper, and scissors, scissors. So that's a total of 9 possibilities. And each of these is equally likely to occur, right? So we're assuming, each player is equally likely to choose any of the 3, we're assuming that is. So each of these outcomes is equally likely to occur. So 1/9. All right. And there's your probability model. Your probability model has to include both of these things: the probability of each occurrence for each outcome, and then the sample space, the total list. All right. Part B: find the probability that player 1 wins the game on the first row. Okay. So there are 3 outcomes for player 1 winning. We can have player 1 rock beats scissors, right? This is player 1, right? Is the first one. So the player 1 wins in that round. Rock beats scissors. And then paper can beat rock, right? So that's player 1 winning. And then we can have scissors. Let's see. Scissors beats paper, right? And that's it. So there are 3 possibilities for player 1, and so the probability that player 1 wins is 3 possibilities out of a total of 9 from the sample space, which is 1/3, or 0.33. All right, so that's it for that one. Pretty easy. All right, so use basic probability rules, including the complement rule and addition rule. Number 5, so randomly select a new vehicle sold in the United States in a certain month. The probability model for the type of vehicle chosen is given here. Now it's a probability model, and remember, for a probability model, the sum of the probabilities must be equal to 1. So how do we know? We know that the probabilities add to 1. So therefore, the probability of a crossover is equal to 1 minus these, right? We have to add these up. Okay, and if we add this up, we get 0.24. Okay, so let me just write 0.24 for the crossover. Find the probability that the vehicle is not an SUV or a minivan. So that means, okay, so probability not SUV or not minivan. So we just have to add those probabilities together, right? These are mutually exclusive, so you just add them. So anything that's not either of those. So we can add passenger car plus pickup plus crossover, and that's it, right? Anything else that's not the others, they go 0.85. All right. Okay, so that takes care of that one. You can also use the complement rule here. If you use the complement rule, you can do 1 minus the pickup truck, right? And then not the pickup truck, I'm sorry. You can do 1 minus the probability of SUV or minivan, which is 1 minus 0.10 plus 0.05. So either one of those will be correct. And then you get 0.85. Okay, that's called the complement rule. So you can use the complement rule, or you could just use the addition rule. Okay, 2 ways of doing that. Use a two-way table or Venn diagram. Okay, so here we got two-way table summarizes response of 120 people to a survey. They were asked, do you exercise for at least 30 minutes 4 or more times per week? And what kind of vehicle do you drive? All right. Suppose one person from this sample is randomly selected. Find the probability that the person drives an SUV. Okay. So that means if they drive an SUV, that means that they can, so we were saying yes for SUV, right? So how many people drive SUVs? Well, we got to add these totals, right? So 15 plus 24, that's 39 for the total. Let me find out all these totals. So this is 45, that's 36. It's good to find the totals when you have the table like this. 27, 52, 48, 68, and we add those together, so we get 120 people. So SUV is going to be 15 plus 24, or 15 plus 24 out of a total of 120, right? Which is 39 out of 120, which is 0.325. Okay. All right, and that's it for that one. Pretty easy. That's the addition rule. Using Venn diagram or using a two-way table. Number 7, in a neighborhood of 32 houses, 18 houses have a swing set, 11 houses have a basketball hoop, and 6 houses have both a swing set and a basketball hoop. And then suppose a household from this neighborhood is selected at random. So let S be have a swing set. Let B mean have a basketball hoop. Okay, so make a Venn diagram of the scenario. So we got, if we were to make a Venn diagram, we have S for swing set and then B for basketball. So we got S here. Let me just do it on the inside since I'm running out of room. All right, so there's, okay, so we got 6 have both, so there's got to be 6 for both, but then there's a total of 18 with a swing set, so it's 18 minus 6 is 12, right? And then there's 11 with basketball, but 11 minus 6, it's 5. All right, 12 plus 6 plus 5 is 11 plus 12 is 23. And remember, there's 32 houses, right? So 32 minus 23 is 9. So there's 9 people that have neither. Okay, and there's your Venn diagram. 9 have neither, 12 have just a swing set, 6 have both, 5 just have just a basketball hoop. Make a two-way table of this diagram. Okay, so what we can do is we can say swing set, no swing set, right? S prime means not, they don't have it. And then we got our total. Then we can have basketball, and then no basketball. And then, of course, our total. We know we're going to have a total of 32. All right, so there's 6 to have both swing set and basketball. There's 12 that have just a swing set but no basketball. There's 5 that have just basketball but no swing set, and then there's 9 that have neither of them. And then we could just add these totals up. All right, and that is our two-way table. Okay. All right, so next one, apply the general addition rule to calculate the probabilities. Using problem number 6. Okay. All right, here. All right, so using problem number 6, find the probability that a person drives a sedan or exercises. So you can, when you calculate this, you can use the general addition rule, or you can use the Venn diagram. Okay, so let me just use the general addition rule. The general addition rule is if you have OR probabilities, you can add the probabilities separately. But then you have to take away what they have in common. Okay, so for example, sedan. If I look at the sedan, there are 45 sedans, those that have sedans, that drive sedans. 45 out of 120, right? So we got 45 sedans out of 120. Plus, then how many exercised? How many? So there's, that said yes, 52 that exercised out of 120. But then we have to be careful that there are people that exercised that also have sedans, right? That also drive. So we have to do sedan and yes for exercise. So that's 25 out of 120. So we just got to take that away. Okay, another way, or you can just say, okay, sedan or exercise. Sedan or exercise means that you're going to do all the exercised ones, right? So these are all the exercises, plus the sedans. But you don't want to count the 25 twice, right? You only want to count the 25 once. So you could do 20 plus 25 plus 15 plus 12. That's another way to do it. So I'm going to show you both ways, and you're going to get the same answer. So you can do that. Either way, you're going to get 0.60 for the probability. All right, so that's the general addition rule, and I also showed you using the Venn diagram without using the general addition rule. All right, so number 9, using problem number 7, find the probability that the household doesn't have a basketball or swing set. Okay, so using this one right here, no basketball, no swing set. Well, that's just 9 people, right? So it's 9 out of 32 people. So that's pretty straightforward. Probability of B prime and S prime. So no basketball, no swing set. That's 9 out of 32, which is 0.281. Find the probability that the household has a swing set or a basketball set. So swing or basketball. Now remember, if you can use the general addition rule, the probability of swing set plus the probability of basketball set minus the probability of both. So you can use those to your advantage if you want to use the general addition rule. So the probability that they have a swing set is, well, it's 18 have a swing set out of 32, right? The probability of basketball, well, according to this, 11 have basketball, right? So 11 out of 32 minus the probability of both, and they said that it was 6 have both, right? Okay, and there you go. And then just add them up. So that's 29 minus 6, and you get 23 out of 32. Okay, another way that you could do it is you could just, if you look at your Venn diagram, you can just add 12 plus 6 plus 5, divide that by 32. So you could do that as well. So I'm going to put that here. Or you could do 12 plus 6 plus 5 over 32. I don't know why I put 120 here. That should say 32. I'm sorry. Sorry about that. Oh, I'm looking at the wrong one. Sorry. Let me, I don't want to mess that up. Sorry. If you go all the way, that's the wrong problem. This one that was not a 120. This one right here. So you can say this one, or you could do 12 plus 6 plus 5 out of 32. Either way, you're going to get the same answer. All right, so lesson 5.3, the last lesson in the chapter. Using problem number 5, given that the vehicle is not a passenger car, what is the probability that it is a pickup? So probability of pickup given a pickup truck, given not passenger car. So remember, the given goes, it goes on the bottom, right? So let me write down the formula for conditional. The probability for conditional is the probability of A given B is equal to the probability of A and B divided by the probability of the given B. Okay, so that's how you calculate that. So we need the probability of pickup truck and not passenger divided by the probability of not passenger. Okay, so let's go back to problem number 5 and see what that probability is. So if I go to problem number 5, the probability of not passenger, okay? Or not pickup, sorry. I think it was not pickup, right? Yeah. Not passenger, I'm sorry. The probability of not passenger. So this is passenger. that means not passenger are these guys, right? So I have to put the given on the bottom. So I need to add those 4 probabilities on the bottom. Now, out of these 4 probabilities, what's the probability of a pickup truck? Well, that's 0.15, right? So, so 0.15 is on the top, and then adding all of these goes on the bottom. Okay, so remember the red is the pickup truck and not passenger car. The black is all of the not passenger car. Okay, so I know it's a little tough sometimes to kind of think about it that way, but that's your guy. So let me show my work here. Okay, so here we got 0.15 out of 0.15 plus 0.10 plus 0.24 plus 0.05. All right, and then if we do that, we get 0.278 for my probability. All right, so that's number 10. Now number 11, using problem number 6, find the probability that the person does not drive a truck given that she or he exercises for at least 30 minutes. Okay, so the probability of not truck given exercises. So again, it's the probability of not truck and exercise divided by the probability of exercise. So the given goes on the bottom, the exercises goes on the bottom. So if I look at the exercises one, let's go to there. Problem, which one was it? This one right here. Yes to exercise, right? So what's the probability of exercise? Well, it's 25 plus 15 plus 12. That's the many that exercise, right? So 25 plus 15 plus 12 out of, that's how many? Out of 120, right? So 25, or so basically 52 out of 120, right? But let me just write down the numbers. 25 plus 15 plus 12 out of 120. And then the probability of not truck and exercise. So not truck and exercise. Not truck, so it can't be this one. So it's got to be these ones, right? So not truck, so sedan, SUV, and then and exercise. So that's 25 plus 15 out of 120. Okay, so that's what we're looking for. All right, so 25 plus 15, go all the way down here. 25 plus 15 out of 120. So that's the probability of that. But notice that the 120s cancel. So it's just going to be the numbers that we add on top and the numbers on the bottom. So if we add this up, we get 40. Let's see. We get 40 out of 52, which is 0.769. Okay, so hopefully that made sense. Practice using this conditional formula, all right? So so you can't really go wrong if you do that. And then, just get used to the formulas because you're going to have the formulas at the end of the day. So as long as you know how to use them, you should be okay. Number 12, an event A will occur with a probability of 0.4. An event B will occur with a probability of 0.25. The probability that both A or B will occur is 0.5. Calculate the conditional probability of A given B. All right, so remember the probability of A given B is the probability of A and B divided by the probability of B. Again, using the formula. The only problem is we don't have A and B. We only have A or B. Okay, so we're going to use the general addition rule. Probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, and we're going to solve for this guy so that we can plug it into there. All right, so if I solve for this guy, the probability of A or B, they said is 0.5, right? So 0.5 equals probability of A is 0.4, probability of B is 0.25. So using a little bit of algebra here, I get this equals 0.4 plus 0.25 minus 0.5. So here I get 6.5 minus 0.5 is 0.15. So that's what A and B is. So then we can plug that in here. All right, and then the probability of B, they told us, was 0.25. Okay, we just plug it in there, and we get an answer of 0.60. All right, that takes care of number 12. All right, we're getting there. Number 13, determine if two events are independent. So you work at Mike's Pizza Shop. You have the following information about the 9 pizzas in the oven. 3 of the 9 have thick crust, and 2 of the 3 thick crust pizzas have mushrooms. Of the remaining 6 pizzas, 4 have mushrooms. Suppose you randomly select one of the pizzas in the oven. Are the events thick crust pizza and pizza with mushrooms mutually exclusive? So let's do a two-way table. And we'll say mushrooms, yes, no. And then we'll do total, of course. And then type of crust. Okay, we'll do that. Thick crust, we have thin crust, and then total. We'll just do a rough two-way table here. Okay, so it says 3 of the 9 have thick crust. So we have 3 thick crust, and then 2 of the 3 thick crust have mushrooms. So yes for mushrooms, that means no have no. One of them has no mushrooms. And then they said 3 of the 9 have, 2 of the, we did that one. Of the remaining 6 pizzas, so there's 6 pizzas left for a total of 9. 4 have mushrooms. So that means 4 thin crust have mushrooms, 2 have none. And so we have 6, 3. So this is a good summary of what we have going on. Are the events thick crust pizza and pizza with mushrooms mutually exclusive? Well, that's easy. Mutually exclusive means that there's no overlap. Is there a possibility of getting... is there any overlap? And the answer is yes. So they're not mutually exclusive. So you could have a pizza with mushrooms and thick crust, right? You can have both of them at the same time. So the events are not mutually exclusive since a pizza can have both thick crust and mushrooms. Okay, so it's not mutually exclusive, but now we're going to see, okay, are they independent, right? So those are two different things. So let's calculate to see if they're independent. To remember, to determine independence, let me just do this off to the side. To determine if A and B are independent, there's a couple ways you could do it. You could say, okay, you can calculate the probability of A given B, and then the probability of A given not B, and see if they're identical, right? You can also calculate the probability of A, and these should all be identical. Okay, so that's one way to do it. So that's how I'm going to do it. I'm going to basically calculate. I'm going to compare this. I'm going to compare this with that, and see if that works. Okay, so I'm going to compare P of A with P of A given B. So in other words, I'm going to compare. So M is mushrooms, and then T is thick crust. Okay, so in this case, let me just say I'm going to say C is thick crust. All right, so we want to see if M and C are independent. So we're going to see, okay, probability of, let's do the probability of M given thick, C. So what's the probability that given a thick crust pizza that it has mushroom? Okay, so given a thick crust pizza, so how many thick crust pizzas we have? We have 3 thick crusts. So out of those 3, how many have mushroom? Well, that's 2. That's easy. 2 have mushroom. So 2/3, right? Let's see. Now let's compare it to the mushrooms. What's the probability of mushroom? Okay, well, the probability of mushroom, there are 6 mushrooms out of 9, right? So 6 out of 9 pizzas, but that's the same thing as 2/3, right? Okay, so that means that these are, they look to be independent, right? They're equal to each other, okay? So since P of M given C is equal to P of M, the two events are independent. That's it. Okay. All right. So that's how you prove independence. All right. So next one, number 14. Use a general multiplication rule to calculate probabilities. So using problem number 10, suppose you randomly select 2 of the pizzas in the oven. Find the probability that both have mushrooms. Okay. So the probability of mushroom for the first one. Let me see. Probability for first mushroom and second mushroom. Okay, so that's what we got to do. So, so in this case, the general multiplication rule is as follows: the probability of A and B is equal to the probability of A times the probability of B given A. That's the formula for the general multiplication rule. Okay. So we just got to do the probability. So in this case, we got the probability that the first is mushroom times the probability that the second is mushroom, given that the first is a mushroom. Okay. Well, okay, so we have, what's the probability of getting mushroom? Well, the probability of getting the first one mushroom is 6 out of 9, right? And then the probability that the second one is a mushroom, given that the first one is a mushroom, well, if we pick one of them as mushroom and we had 6 mushrooms, how many mushrooms do we have left? Well, we have 5 mushrooms left, right? So we have 6 mushroom. I selected one of them, so now I got 5 left, right? So then the odds of selecting another mushroom is 5 out of 8, because now we have 8 pizzas in total. So we have 6 mushrooms and 9 pizzas in total. But if I select a mushroom, then that's 5 mushrooms out of 8 pizzas, right, in total. So it's got to be 5 out of 8. The odds change, okay? So I now got to multiply those together. If I multiply them, I get 0.417 as a decimal. All right. That takes care of that one. So let's look at number 15. Use a tree diagram to model a random process. Many employers require prospective employees to take a drug test. A positive result on this test suggests that the prospective employee uses illegal drugs. However, not all people who test positive use illegal drugs. The test result could be a false positive. So even if you didn't take the drugs, you could still test positive, but it would be a false positive. A negative test result could be a false negative if the person really does use illegal drugs. Suppose that 4% of prospective employees use drugs and that the drug test has a false positive rate of 5% and a false negative rate of 10%. You can ignore that number there. Imagine choosing a prospective employee at random and draw a tree diagram for this process. So we're selecting a random employee. And they either use drugs or they do not, right? So drugs, no drugs. And then it says that how many employees use drugs? It says 4% of prospective employees use drugs, suppose. So that means that the probability that you select someone that uses drugs is 4%, which means that this has to be 96%. Most of the employees don't use drugs. All right, so now if you, so now for each of these, they could either test positive or test negative, right? Now, if they use drugs, the probability that they test positive or that they test negative, so if they use drugs, the probability that they test negative is 10%, right? It says, suppose 4% of people use drugs and that the drug test has a false positive rate of 5%, false negative rate of 10%. So that means that if they use drugs, if they test negative but they use drugs, then that's a false negative, right? So the probability that they test negative if they use drugs is 10%, right? which means that the probability that it tests positive if they do drugs is 90%. So you got to understand that process. Now, false positive means that it says that they test positive, but they didn't actually do any drugs. So that's over here, right? 5% that they test positive, but they didn't do drugs, which means 95% that they test negative and they did no drugs. All right, there's your tree diagram. So find the probability that the drug test is positive, okay? So the probability that it's positive. Well, to find the probability that it's positive, you would have to do this pathway for positive and this pathway for positive, right? So the probability of positive are these two pathways. Okay, so in other words, they could be they could use drugs and be positive, or they could not use drugs and be positive. Okay, so it's the probability of drugs and positive. I'm just gonna use the plus sign for positive. Okay, drugs and positive plus probability of no drugs and negative. Okay. Now, when you're doing each pathway, you multiply the probabilities along the way. So 0.04 times 0.90. Okay, so 0.04 times 0.90 plus. Then you want to do no drugs and, oh, why did I put negative here? I'm sorry, this should say positive, my bad. We're doing the probability of positive. So it's drugs and positive or no drugs positive, okay? I didn't want to confuse you there. So we got 0.04 times 0.09 or 0.90, and then we got 0.96 times 0.05. Okay, those are the two positive routes. All right, and just do that and get your answer. You get 0.084. So you have a 8% chance that you're going to have a positive drug test result. Regardless of whether they do drugs or not, you're going to get 8.4% chance positive. If the prospective employee's drug test result is positive, find the probability that she or he uses illegal drugs. That's important to know, right? Like if they test positive, what are the chances that they actually did do illegal drugs, right? So that's important. So the probability that they use drugs given a positive test. All right, so remember the conditional probability is the probability of both divided by the probability of given the positive test result. Now we just found the probability of positive result, 0.084, so we can do that over here. We just did that here. And the probability of drugs and positive, we did that, guess what? We did that over here, drugs and positive, you see? So really that's the 0.04 times 0.90 number. So that part over the answer that we got earlier. And you get 0.429. So there's almost a 43% chance that they actually did use illegal drugs if you got a positive test result. All right, so there we go. Let's look at number 16, another tree diagram problem. Suppose a particular class has 30 students in it, 17 girls and 13 boys. The teacher uses a calculator to select 2 students at random to solve a problem on the board. Okay, so you use a tree diagram. So this is a 2-stage process. You can have a boy or a girl, and then for the second student, you can have a boy or a girl, right? Now, if you choose a boy, there's 13 out of 30 boys. 13 out of 30 students are boys. 17 out of 30 students are girls. Now, if you choose a boy, then remember, you're going to have 12 out of 29, right? 29 kids. Once you choose one of the students, you have 29 students. Once you choose one boy, then you have 12 now. But you still got 17 girls if you choose a boy, right? Because you didn't take away from the number of girls. But there are still only 29 students. Now, if you chose a girl, then that's 17 out of 30 chance, right? So now if you choose a girl, then now you have 16 girls out of 29. But you still have 13 boys out of 29. You didn't choose any boys for the first time. You just chose a girl, and then now you're going to choose a boy. So those are your odds for each branch. What is your probability? So what is the probability that both students are boys? So that means probability of boy and the first is a boy. So boy 1 and boy 2. Basically, I'm just going to do that. All right, so it's the boy 1 and boy 2. You're basically just doing these two, right? I'm doing those two probabilities. Okay, so 13 out of 30 times 12 out of 29. And that's 0.179 approximately. What's the probability of selecting a boy and a girl? So probability of, so now if you select a boy and a girl, that means you can have a boy for the first one and a girl, right? Or you can get a girl first and then a boy second. Does that make sense? So you get a boy for, let me just say boy and girl plus girl and boy. I'm just going to do that. Okay. So either one of those, boy first then girl, or girl first then boy. So in either case, you're going to get 13 boys out of 30 times 17 girls out of 29. Okay, so that's for boy and girl. So that's this pathway right here. Multiply those along the way. And then the second one is girl, then boy. Multiply those along the way. All right, and then so when you do that, you get 0.508 for your probability. All right, so given that the second student is a girl, what is the probability that the first student was also a girl? So the probability that the second student was a girl, given that the first student was a girl. Okay, so now this is the probability that the second one was a girl and the first one was a girl, divided by the probability that the first one was a girl. Okay, now the probability, let me make sure I get this right. Given that the second student is a girl, okay, so this should be G2, second student is a girl. I did that incorrectly. So this would be G1 and G2, and then this is G2. The given goes on the bottom. Okay, so what's the probability of G1 and G2? So that's girl and girl, right? So 17 out of 30 times 16 out of 29. So let me do that here. And then what's the probability of getting a girl for the second one? So getting a girl for the second one means you could get boy, then girl, or girl, then girl, right? So you can get either of those. 13 out of 30, 17 out of 29, or 17 out of 30, 16 out of 29. 13 out of 30, 17 out of 29. So you can get a boy, then a girl, or you can get two girls. So a girl and then another girl. What was it? 17 out of 30? Yeah, you can get a girl and then the second one's a girl, 16 out of 29. All right, and just do the math. You got 0.552. All right. Okay. Takes a lot of practice with the formula. So just be mindful of what you're plugging into the formula and use your tree. The tree is very useful to have. All right, so 17. On Mr. Casper's debate at Thunderbird High School, 15% of the members are sophomores, 30% are juniors, and 55% are seniors. A team member is selected randomly to give the closing argument for the team. If a sophomore gives a closing argument, the team has a 0.3 probability of winning the debate. If a junior gives a closing argument, it's 0.6. If a senior closes, the probability of winning is 0.8. Okay, find the probability that the team wins the debate. Use a tree diagram. So I'm just gonna quickly make a tree diagram. So we got sophomore, we got junior, and we got senior. Now, it says 15% of the members are sophomores, 30% are juniors, and 55% are seniors. And then, so now, if the sophomore gives an argument, then they could either win or lose, right? And it says we have a 0.3 chance of winning if a sophomore gives a debate, gives a closing argument, and 70% chance of losing. For a junior, we have a 60% chance of winning and a 40% chance of losing. And senior, we have a 80% chance of winning and 20% chance of losing. All right, so there you go. There's a tree diagram. Find the probability that they win. Okay, so if they win, that means that they could have sophomore and win plus the probability of junior and win, or they could have a senior and win, right? So either one of those will allow them to win. So sophomore and win, that's this route right here. So that's multiplying those two together, okay? So 0.15 times 0.3. Sorry, I gotta multiply those. Now, plus, now junior and win. So that's gonna be junior and win. So 0.30 times 0.60. All right. And then senior and win is 0.55 times 0.20 for, 20 is losing, 80% chance of winning. And you multiply them, add them up together, you get 0.665. That's a chance of winning the debate. Okay, all right, so there you go. That takes care of that one. So learning target 5.3.5, use the multiplication rule for independent events. Harris Interactive reported that 33% of U.S. adults believe that finding and picking up a penny is good luck. Assuming that responses from different individuals are independent, what is the probability of randomly selecting 10 U.S. adults and finding at least one person who believes that finding and picking up a penny is good luck? So, all right, so at least one person. So that means 1 or 2 or 3 or 4 or 5 people, right? So on and so forth. So the opposite of getting at least one person is getting none of them. Okay, the opposite of getting 1 or 2 or 3 or 4 or 5 people that believe in a penny for good luck is the probability of getting none. Okay, and that's easier to do. Okay, so we're going to do the probability of at least one believe is 1 minus the probability that none believe. Okay, and it says that 33%, and then they said that the probability, we know that the probability that they believe is 33%, right? So let me just do that. So 1 minus 0.30. And we know that the probability, let me just write here, probability that the 1 believes is 0.33. Probability that 1 does not is 1 minus that, right? Is 0.67%. Or 67%. Okay, so the probability that, and we have how many people? We have 10 US adults, right? So that means the probability, we have 1 minus, we have 0.67 chance that they don't believe, but we have to do that for 10 people. Okay, so again, 10, we have to say, okay, 1 minus the probability that they don't believe, and the second person doesn't believe, and the third person doesn't believe, and the fourth person doesn't believe, so on and so forth, that none of the 10 people believe, right? But remember, if you have and not believe, and probabilities multiply. Okay, you have to multiply the probabilities. So if I have 10 non-believers, I have to multiply those people together, right? I'd have to multiply them 10 times. I have to do 1 minus probability of not believer, probability of not believer, times probability of not believer, 10 times. In other words, it's this raised to the 10th power, right? Which is why I have 0.67 raised to the 10th power. All right, so it's going to be 1 minus that to the 10th power, which is 0.98177. Okay, I just put a lot of decimals there, but you can round it. It's fine. All right, so 19. Sharon finds out that if she makes it to her train at 8 a.m. each day, she has a 20% probability of missing the train. What is the probability that she catches the train for 3 consecutive days? So 3 days in a row, right? Remember that the probability that we can do the, they said, all right, so the probability that we want the probability that she makes the train, she catches it, and catches it on the first day, and catches it on the second day, and catches it on the third day, right? 3 consecutive days. So that's the probability that she catches it times the probability that she catches it the second time, times the probability that she catches it the third time. So it's basically the probability that she catches it to the 3rd power. Okay? But what's the probability that she catches it on a particular day? Well, it says she has a 20% chance of missing the train, right? So the chance of missing, the opposite of missing the train is you make the train. So it's 1 minus the probability that, in other words, the probability that she catches a train is 1 minus the probability that she misses the train, right? And the probability that she misses the train is 0.20%. So it's really 80% that she catches the train, right? So then we can plug that into there, okay? So we got 0.80 raised to the 3rd power, which is 0.512. Okay, guys. All right, that's going to do it for the video, guys. I hope you found this useful and informative. And as usual, I'll see you in the next one.